We're going to be going over exam 1. This is just the front page of the exam. We'll start with number 1. Get my key out. Okay, so here for each of the following groups of pure substances. Now remember, these are pure substances, and so this question deals with intermolecular forces. You need to identify the strongest intermolecular forces in these sets of 3 substances and then put them in order from strongest to weakest. And then we're going to also discuss how the strength of the intermolecular forces affects the parameter that's listed there, vapor pressure and heat of fusion. So we're going to start with A, which is vapor pressure. We're going to circle the highest value and underline the lowest value. Remember that vapor pressure increases as the strength of the intermolecular forces decreases. Now here, the molecule on the left is propane, and that is nonpolar, so it exhibits only London dispersion forces. The one in the middle is an alcohol. It has a hydroxyl group, OH, which means it can hydrogen bond. And then the molecule on the right is also nonpolar. It exhibits only London dispersion forces. So when we're comparing the strength of those London dispersion forces, the smaller molecule on the left is going to have weaker London dispersion forces because it is less polarizable than the molecule on the right, which is butane. And so of these 3, the weakest intermolecular forces is the molecule on the left, propane. And so it's going to have the highest vapor pressure. We're going to circle that. And the molecule with the strongest intermolecular forces is going to be butanol, the alcohol, which exhibits hydrogen bonding. So we're going to underline that. And remember, vapor pressure goes up as the strength of the intermolecular forces goes down. That's because weak intermolecular forces make it more easily escape into the gas phase, which is going to raise the vapor pressure. Part B, heat of fusion. Heat of fusion increases as the intermolecular strength forces increases. And so the molecule, the first molecule, HCl, is polar, but it cannot hydrogen bond. And so that molecule, HCl, exhibits dipole-dipole interactions. Magnesium oxide exhibits ion-ion interactions, or ionic bonding. And methane is nonpolar, so only London dispersion forces. Of those 3, ion-ion interactions are the strongest, so magnesium oxide will have the highest heat of fusion. Remember that ionic compounds are typically solids, and so if you imagine the amount of heat required to melt a salt or an ionic solid, then that would be really high, right? So that's going to tend to have the strongest intermolecular forces, the highest heat of fusion. And then the one in the middle is going to be HCl, which exhibits dipole-dipole interactions. And then the weakest intermolecular forces are the London dispersion forces exhibited by methane. So that one has the lowest heat of fusion. Number 2, consider the information provided at the top of the exam. So if we go back to the exam, the front page, that's going to be this table here. So we're going to use that information, and we're going to convert liquid ethanol at a certain temperature to gaseous ethanol at 95 degrees. So that means we're going from the liquid to the gas phase, which is vaporization. So we need to go back and identify what the temperature, the boiling temperature is, the boiling point, so that we can figure out how many steps there are in this problem. So if we go back, the boiling point is here, 78.4 degrees. If we come back, that is the temperature that we're starting at. So we're starting at the boiling point, which means we don't need to raise the temperature to the boiling point because we're already at the boiling point. But we do still need to vaporize the substance. So we're going to start by vaporizing the substance. That's going to be step 1. That's at 78.4 degrees. This flat line here is the vaporization. So heat is added, but the temperature doesn't change because it's converting the liquid into the gas. And then the second step is to raise the temperature of the gas up to 95 degrees. So we're going to do this in 2 steps, step 1 and step 2. Step 1, we're going to vaporize 19.5 grams. Q equals number of moles times the heat of vaporization. We're going to convert 19.5 grams into moles. Here, 0.423. We're going to multiply that number by the heat of vaporization from the front page, which is here, 38.56. Moles cancel and you end up with 16.3219 kilojoules. Step 2, we're increasing the temperature. So whenever you're increasing the temperature, you want to figure out the heat, or Q, involved in that. The equation is Q equals mc delta T. So the m is mass. A lot of people put moles on that, but m is mass. And you know that because up here, your specific heat is in joules per gram degree Celsius. And so you have to multiply by mass in grams in order to cancel this grams out. So 1.416 is our specific heat. We plug that in, and then the difference in temperature is 95 minus 78.4, which works out to be 16.6 degrees Celsius. So the second Q is 458.3592 joules. We're asked for the heat in kilojoules up here, so we need to convert our second heat down here into kilojoules so that we can add it to the first Q we did. So that's 0.458359 kilojoules. And then I'm going to erase some stuff up here so that I can make room to calculate the total Q. So Q total equals Q1 plus Q2. Q1 was here, 16.3219 kilojoules. Q2 is our new converted 0.458 kilojoules. We add those together and we get Q total is 16.7803 with some more digits. Now when we figure out significant figures, we're going to do that in orange. So here we have 3 sig figs multiplied by, this probably has 4 sig figs. That means that 0.423 has 3. 0.423 has 3 sig figs multiplied by the heat of vaporization, which has 4, which means that this number of kilojoules here, 16.3, is accurate to this tenths place, 0.3. And then in the Q equals MC delta T part 2, 19.5 has 3 sig figs, 1.416 has 4 sig figs, and then 16.6 has 3 sig figs, right? It's accurate to that tenths place. That first subtraction step gives you 16.6, which means that our second step is accurate to 3 sig figs. So now when we add these two together, we have this number here, 16.3, which is accurate to the tenths place. We're adding to that 0.458, which is accurate to the tenths, hundredths, thousandths place. So now we need to round it to 1 digit after the decimal because that's the least significant place here. So it's going to be accurate to that tenths place. That's 7. So we need to round it to 16.8 kilojoules. And we're going to circle that, and that's going to be our answer. Now we're going to move on. Calculate heat in kilojoules required to sublime 1 gram of ethanol. Now this little picture here is to remind you that when you go from the solid to the liquid, that's the heat of fusion. When you go from the liquid to the gas, that's the heat of vaporization. So this is enthalpy on a vertical scale. And this is just to remind you, when we talked about this in class, what we said is that once you know these two values, you know the heat of sublimation because that is just the sum of those two, right? Hess's law taught us in Chem 101 that all that matters is the initial state and the final state. Right? It doesn't matter if you go there all in one step, like we're doing here with the green arrow, or if you go in 2 steps, like we're doing with the red arrow and the blue arrow. If this total is just equal to the sum of these two numbers. Okay, so the first step in this problem is the one that's the hardest one to remember, and that is that the heat of sublimation is the sum of the heat of fusion and the heat of vaporization. So when you add those two together, get those on the front page, that's here and here. We're going to add those two up and you get 43.46 kilojoules per mole. Now we need to calculate the moles of ethanol in 1 gram. 1 gram divided by the molecular weight, and you get moles, 0.0217 moles of ethanol. Multiply that by the heat of sublimation that we calculated in step 1, and you get 0.94338. And then now we're going to do the sig figs in orange. So 4.9 plus 38.56. This is accurate to the tenths place, this 9. This 38.56 is accurate to the hundredths place. So when you add these two together, it's only accurate to the tenths place. So 43.46, this number has 3 sig figs. Step 2 here, when we're calculating moles, 1.0 grams only has 2 sig figs. So that means that our moles only has 2 sig figs. So this number has 2 sig figs, this number has 3 sig figs, which means our final answer should only have 2. So we're going to round it to that 4.94 kilojoules. We'll circle that. Number 3, consider the following cooling curve for 1 mole of a particular substance. So when we look at the cooling curve, we need to really think about what's present here. This first line that comes down from 80 degrees. That's a gas phase because we start off with the highest temperature and then we cool it down. This is liquid and gas, and then the liquid lowers the temperature. And then this line is where the liquid and solid are interconverting, and then the solid is down here at the bottom. So the flat lines are the phase transitions, right? This first one here is condensation. This second phase transition here is freezing. So we need to really understand the graph before we can answer any of the questions. So part A says, what is the approximate boiling point, or TB, of this substance to the nearest degree Celsius? So that value is going to be here where this flat line is, right? So where the liquid and the gas interconvert, whether it's condensation or boiling or evaporation, whatever, doesn't matter. This line represents the boiling point in degrees Celsius, so it's somewhere between 60 and 70. I think I estimated that to be about 66 degrees, but anywhere near there is fine. Part B, what phase or phases are present in the dotted line labeled A? That's here. Right, I didn't color that on purpose so that we could see it. That's here. And that's a gas. What phase or phases are present in the dashed line labeled B? That's here. And that's the liquid and the solid present together. Part D, consider the dotted line labeled A and identify which of the following constants affect the slope of this line. So we're looking at this line. So this is where we're changing the temperature of the gas. So the gas is losing heat, therefore decreasing in temperature. So whenever there's a temperature change, the equation that relates to that is Q equals mc delta T. Here it says we have 1 mole of a particular substance. So the mass is something that would influence it, but that's not on our list. Okay. So when we look at all the different items on our list, that's heat, that's along X here, and then Y is our change in temperature. So when you look up here, M or C, C is the specific heat, those are the only things that could possibly influence this. And so it has to be one of these specific heats at the bottom. It can't be heat of fusion, it can't be heat of vaporization, it can't be heat of sublimation. Heat of fusion would be related to the length of this line here where the liquid and the solid are present. So that would be related to the length of line B. And the heat of vaporization would be related to the length of line A, right? So the larger the heat of vaporization, the longer this line will be. But we're talking about this sloped line here, A. Okay, so it has to be a specific heat, and it's definitely the specific heat of the gas, not the liquid or the solid, right? The specific heat of the liquid would affect the slope of this green line, and the specific heat of the solid would affect the slope of this gray line. And so the only possible answer is the gas, the specific heat of the gas. I think each of these, let's see, part A was worth 1.5 points, B was worth 1.5 points, C was worth 1.5 points, and D was worth 1.5 points. So that adds up to 6. Let me know if you have questions about the points. Number 4, consider the phase diagram below. Answer the questions that follow. So the first thing we need to do is we need to label our phase diagram with the solid and the liquid and the gas, which is here. It's pretty important that you can do this. If you did this incorrectly, then you would have gotten a lot of this wrong. And it's just, you know, solid is present at either low temperature or high pressure, right? And the gas is present at either high temperature or low pressure. And so either one of those ways to remember. A few of you had these mixed up, but it's pretty important that you remember where they go. What is the approximate normal boiling point of this substance in degrees Celsius? So normal boiling point means where the liquid converts to a gas, and it is, the normal word means at 1 atmosphere. So we go across to 1 atmosphere, we draw a line, we go to the separating line between liquid and gas, and that is approximately 400 Kelvin. The 1 atmosphere part, remember, relates to the word normal. 400 Kelvin minus 273 will give you the temperature in degrees Celsius, which is approximately 127 degrees Celsius. Which line denotes sublimation in the graph above? So that's from the solid to the gas phase, so that would be line AB. Part C, which phase transitions, if any, occur if the pressure were increased from 0.5 to 3 atmospheres at a constant temperature of 200 Kelvin. You should identify all phase transitions. So if we mark on here 0.5, so we're going to change the pressure from 0.5 to 3 atmospheres. So we start here at 0.5, we go up to 3, and it appears that we first transition from a gas to a liquid phase and then from the liquid to the solid phase. You don't go straight from the gas to the solid, and so you can't write deposition. You need to include both phase changes. So the first one is condensation, gas to the liquid, and the second one is freezing, the liquid to the solid. If we go back briefly to here, part A was worth 2 points. I gave 1 for converting from Kelvin to degrees Celsius and 1 for identifying the point. And then the AB line was worth 2 points, and each phase transition was worth 1.5 points. Now if we move on to number 5, these were worth 2 points apiece. So we have ammonia in water. So remember, these are solute-solvent interactions, and so these are the interactions that form when you mix the solute, which in this is the first one listed, with the solvent, which is the second one listed, which is water for all 3 of these. So ammonia is a polar molecule, and it can hydrogen bond because it looks like this. So ammonia can hydrogen bond, water can hydrogen bond, which means they can hydrogen bond to each other, right? Just like this. So this would be the solute-solvent interactions for ammonia mixed with water. So you would write hydrogen bonding. Potassium chloride in water. So potassium chloride, remember, dissociates. This is the ion-ion interactions that would exist in the crystal lattice. But then those are going to separate when water is added, and then you're going to form ion-dipole interactions. The ion is either potassium or chloride, and the dipole is the water molecule. So ion-dipole is what we're going to write for potassium chloride in water. Now the last one, CH3Cl, chloromethane. Chloromethane, if you look at my molecule here, is polar, right? Remember, it has to be, if it's at all asymmetrical, like this is, we have 3 hydrogens but 1 chlorine, that means that the dipoles do not cancel out. This is a polar molecule, but it cannot hydrogen bond. And so there's an overall dipole like this. So this is polar, but cannot hydrogen bond. And therefore, if we draw another one, remember there's a partial positive and a partial negative charge. That would be a dipole-dipole interaction. Dipole-dipole. And that's true between itself and itself, or between itself and water. So you can see here, even though water can hydrogen bond, because chloromethane cannot, then you can't put hydrogen bonding here. You have to put dipole-dipole. Right? So water is one dipole, and the chloromethane is the other dipole. And there's our dipole-dipole interaction. Those were 2 points apiece. Let me know if it's still confusing. Number 6. So we're preparing a solution of ammonium sulfate by dissolving 20 grams of ammonium sulfate in 80 grams of water. We have the density of the resulting solution. Part A is to calculate the molality. So molality is moles of solute per kilogram of solvent. The solvent is water, the solute is ammonium sulfate. So we're going to convert 20 grams into moles, which is 0.151 moles. We'll put that in the top. Kilograms of solvent, 80 grams of water is our solvent. So if we convert that into kilograms, it's 0.08000 kilograms. And you end up getting 0.151,33859 divided by 0.08 kilograms. And that gives you 1.8917 molal. Now, if we think about significant figures, that's what we're underlining here. 20.00 grams has 4 sig figs, and this molecular weight has probably 5 sig figs. And then that means that our moles has 4. We'll put that in the numerator, so this has 4. And then 80.00 grams, or 0.080000 kilograms, 000 kilograms, sorry, has 4 sig figs as well. So the numerator has 4, the denominator has 4, which means our answer should have 4, 1.892 molal. Let's see. This is worth 5 points. You got a point for the molecular weight of ammonium sulfate. You got a point for dividing by the molecular weight of ammonium sulfate. You got a point for converting grams to kilograms here. You got a point for plugging numbers into this molality equation. And then you got a point for the answer. That should add up to 5. Part B, mole fraction. You should start by writing the equation for mole fraction, moles of ammonium sulfate divided by total moles. The total moles is going to be ammonium sulfate plus moles of water. Moles of ammonium sulfate you're going to get from part A, and then moles of water we're going to determine from the 80 gram mass that we're given in the problem. So 80 grams, and we'll divide that by 18.016 grams per mole, and you get 4.44 moles of water. And you plug those numbers back into the mole fraction equation. Remember that the denominator is total moles, not just moles of solvent. Moles cancel, and you end up with no units. And we get 0.03295888. And we have to figure out significant figures. We'll do that in green. 80.00 has 4, 18.016 is most likely accurate to this hundredths place, which means 4 sig figs in our moles. So we have 0.1513, that's accurate to this 3, that's accurate to this 3. That means our denominator is accurate. That's 4 digits after the decimal, that's 3 digits after the decimal, which means our sum is 3 digits after the decimal. This number, it has 4 sig figs, 4.591, it's accurate to this 1. This has 4 sig figs, so the numerator has 4, the denominator has 4, which means our answer should have 4. I accidentally wrote 3 there, but in a second I hope that I erased it and replaced it with a 4, so we're going to round that to 0.03296. This one is also worth 5 points, sorry. So you get a point for plugging in the 1.151, the moles from part A. You get a point for the molecular weight of water, and then also for dividing by the molecular weight of water. So this step is really worth 2 points. And then you get a point for this sum down here, right? And then the point for the answer should make 5. Part C, determine the molarity in this solution. So we have moles of solute divided by liters of solution. Again, the numerator is from part A. Volume of solution is the mass of the solution divided by the density of the solution. The mass of the solution is 80 plus 20, so 100 grams. Divide by the density, and you get 89.6539 milliliters, which is the same thing as 0.0896539 liters. That goes in the denominator. So the molarity is, you plug those numbers in and you solve. We're doing sig figs here. 100.00 has 1, 2, 3, 4, 5. This number has 5, which means this number has 5. And here we have 4 sig figs from part A, and this number down here has 5 sig figs, which means our final answer should have 4 sig figs. 1.688 molar. We'll circle that. Again, this problem is worth 5 points. So you get a point for adding these two together to make 100 grams. You get a point for dividing by the density to get milliliters. You get a point for converting milliliters to liters. And you get a point for plugging those things back into the equation, and a point for the answer. So that makes 1, 2, 3, 4, 5. Let me know if you have questions about your points. Now we're going to do our molecular weight determination using colligative properties. Remember that molecular weight is grams per mole, so we know that the mass is 30 grams. We just need to figure out how many moles that represents. We're going to calculate moles from the freezing point depression information. Does not dissociate in water means that the I value, the Van Hoff factor, is a 1. So we plug everything into our freezing point depression equation. We need Kf, that's going to be on the front page. That's here. We plug that back in. And we solve for molality, which is here. So molality in this case is going to be 0.9247 molal. If you remember, separate that into its base units, moles per kilogram. Multiply. Remember, this is mass of the solvent. A lot of people thought this was just kilograms of anything. Remember that molality is moles of your solute, which in this case is quinine, divided by kilograms of the solvent, which in this case is water. So you can't mix up the mass of the quinine and the water. You have to keep track of what's the solute and what's the solvent. So the goal of this problem is you're given the mass of the solute, and you know that that's going to go here in the numerator of our molecular weight. And you need to figure out how many moles that 30 grams represents. And that's what this data are going to tell you, right? So you're going to plug those numbers in. And then when you have moles per kilogram, moles of quinine per kilogram of water, you need to multiply by the mass of the water, not the quinine. So you have 100 grams of water. So that is 0.1000 kilograms. Kilograms cancel, and you have 0.09247 moles that goes here in the denominator. So the molecular weight is 30 divided by that, which gives you 324 grams per mole. And it has three significant figures, and that is because all the numbers here seem to have three sig figs. 1.72 has 3, 1.86 has 3. This 1 is exact, so that means this 0.9247 is accurate to this 4. The 30.0 has 3, and then this number here should have 3. And so at the end of the day, your molecular weight has 3. And those are the sig figs that I've written in here, right? I've underlined the least significant figure, and I've reminded you that the 1 here is exact, the Van Hoff factor, the theoretical Van Hoff factor, and then all the accuracies are underlined. Oh yeah, points. Oops. What are we going to do about points there? Let me figure out points. So here, this was worth 6 points. You got a point for plugging things in to this equation correctly. You got a point for solving for molality here. You got a point for converting grams to kilograms here, this blue line. You got a point for multiplying by 0.1 kilograms to get moles. And you got a point for dividing grams divided by moles here to get the answer, which was also worth a point. So that should add up to 6. Now we're going to move on to number 8. Number 8 is worth 2 points apiece. Okay, so consider the following sets of substances. Now, these are solutions, okay? And so this is a colligative properties question. And the colligative properties in this case are going to be boiling point elevation and vapor pressure lowering. So we're going to circle the highest value and underline the lowest value. So boiling point increases as concentration increases. Now, if you look at each one of these solutions, potassium nitrate dissociates into 2 particles per mole of potassium nitrate. So 1 molal solution has 2 molal particles. Sucrose is a non-electrolyte, so it has 1 molal particles. Potassium phosphate dissociates into 4 particles for each formula unit of potassium phosphate, which means that a 1 molal solution is 4 molal particles. Strontium chloride dissociates into 3, 1 strontium and 2 chlorides, which means this is overall 3 molal particles. So that means we're going to find the one with the highest concentration, which is potassium phosphate, which is 4 molal. And we're going to circle it because it has the highest boiling point. And we're going to underline sucrose because it is the lowest concentration and therefore has the lowest boiling point, closest to pure water. Now vapor pressure, remember that vapor pressure goes down as concentration goes up, and that's because the solute particles get in the way, right? The solvent can't evaporate as easily, so it doesn't have as high a vapor pressure because the solute particles are getting in the way. So now when we look at concentrations again, water is basically 0 molal particles. Sodium fluoride is 3 molal particles because we have 1.5, and we need to multiply that by I of 2 because it dissociates into 2 particles per formula unit. So 1.5 times 2 is 3. 0.5 times 5 now, magnesium nitride dissociates into 3 magnesiums and 2 nitride ions, which means there's 5 ions per formula unit. So 0.5 times 5 is 2.5, and finally aluminum fluoride dissociates into 4 particles. 4 times 1 molal is 4 molal. So now we're going to find the one with the lowest concentration, and that should have the highest vapor pressure, and that's water, and then the one with the lowest, with the highest concentration should have the lowest vapor pressure, and that is aluminum fluoride. So those were worth 2 points apiece. Let me know if it's confusing. Number 9. This is a related rates question. So we're going to calculate the rate of change of oxygen given the rate of change of rate of formation of carbon dioxide. So we have the balanced equation at the top here. And so we can write the related rates expression, which is here, rate of reaction equals -1/2 change in acetylene over change in time, -1/5 change in oxygen over change in time, equals +1/4 change in CO2 over change in time, equals +1/2 change in water over change in time. And then, of course, the numbers down here and the fractions come from the stoichiometric coefficients. The reactants are negative because they decrease in concentration over time, so they should have a negative rate of change. And the products are positive because they should have a positive rate of change. They should increase in concentration. So now we're trying to calculate rate of change of oxygen, which is this number here, this delta O2 over delta T. We're given the rate of formation of CO2, and that's this number here, delta C over 2 over delta T. So I'm going to circle the part of this related rates expression that matters, and that is this part. Now we're going to rearrange it. I'm going to rewrite it down here, and I'm going to plug in numbers, right? So the rate of change of oxygen is what I'm solving for, and I've plugged in numbers. So I've just moved this down here, and I'm solving for delta O2 over delta T, and I plugged in the number, the value, rate of formation of CO2 is this green that I'm circling, and that's what I plugged in there, right? And then I'm solving for rate of change of oxygen, which is here. I'm going to circle that in red. So when we solve for that, we get -5.31 times 10 to the minus 2 molar per second. It has 3 sig figs because the original number has 3, and this 5 and this 1/4 are exact numbers, so they don't change your sig figs. Now the lower part, the part B, is calculate the rate of reaction. Rate of reaction is in my related rates expression. A lot of people forget that that's how the related rates expression begins. So whenever you see rate in any kind of table anywhere, that means this rate of reaction. Okay, so the rate of reaction is always normalized to be the same value regardless of which of these reaction components you have monitored. So the rate of reaction is simply 1/4 delta CO2 over delta T, and so you just take that number, you divide by 4, and you get 0.0106 molar per second. It has 3 sig figs, just like the 4.25 times 10 to the minus 2 number. Parts A and B, they were each worth 3 points. You get 1 point for the related rates expression. You got 1 point for the math that you did to solve for that, and then 1 point for the answer. And then part B was the same way, 1 point for this related rates expression, 1 point for doing the math correctly, and 1 point for your answer. We're going to move on to number 10. So we have a rate, and we know the reaction is first order in A, first order in B, and zero order in C. So we're going to choose which of the following changes would result in no change in the observed rate. So we're going to take each one at a time. Doubling the concentration of A, because it is first order in A, would also double the rate. It would have the same effect on the rate. So we're not going to pick that because it definitely changes the rate. Doubling the concentration of B would certainly double the rate because it is first order in B. So we're going to cross that out too. Zero order in C means that it doesn't matter what we do to C because it does not influence the rate at all. It must not be involved in the rate determining step. And so doubling the concentration of C, even if you quadrupled it times 10 times a million, it doesn't matter. It will not affect the rate of the reaction. So this has no effect on the rate. So we will certainly check that because it does not change the rate. The fourth one, doubling the concentration of A at the same time as having the concentration of B. So because they're first order, if you double the concentration of A, that would double the rate. But at the same time, you're having the concentration of B, which would have the rate. So if you take those two together, a doubling effect along with a halving effect means that it has no change on the rate. The change is 1x. So you're going to check that as well. Doubling the concentration of A and having the concentration of C, because C has no effect on anything, this would effectively have the same this would have the same effect as number 1, just doubling the concentration of A. So the rate would double, so we're going to cross that out because the rate doubles. Doubling B and having C is just like A and is just like the one before it, right? So again, it's just like the second one. If we double the concentration of B, and then this issue with whatever we do to C has no effect. So this doubling B and having C is going to be the same thing as just doubling B, which would double the rate. So we're going to cross that out too. Doubling the concentration of B and having the concentration of A is just like what we did up here, right? Since they're both first order, doubling B would double the rate, having A would halve the rate, and so when you put those two together, a doubling and a halving has no overall effect. So we're going to check that as well. And then the last one, doubling the concentration of A and C, and at the same time having the concentration of B. Remember, C has no effect on anything, so it doesn't matter what you do to C. So this one here, this last one is the same as this one up here, doubling A and having B. If you double A and have B, and then whatever you do to C doesn't matter. And so that's going to have the same effect. So we're going to check that one as well. These were worth half a point each, and so that adds up to 4 total. We're going to move on to number 11, which is our rate law question. So here we're going to compare experiments 1 and 2 for the concentration of ClO2 along with the effect on the rate. And then we're going to compare experiments 2 and 3 for how the effect of the concentration of hydroxide. So remember that the rate law has this form. We're trying to figure out what are x and y. And so if you compare experiment 2 to experiment 1, if we go from 2 to 1, we're basically tripling the concentration of chlorine dioxide. And if you look at the effect on the rate, it is 9-fold higher. And then if you look at the concentration of hydroxide between experiments 2 and 3, we are also tripling that, and then that triples the rate if you look at the observed effect on the rate. If you're not sure, if you can't see that, then you can always plug the numbers in. Remember that 9 is the same as 3 squared, which means that this is second order in chlorine dioxide. And then if you compare experiments 2 versus 3, then you get 3s for both of them. 3 is 3 to the first power, which means it is first order in hydroxide. So we're going to plug those numbers in here, right? ClO2 becomes a 2, and then hydroxide is to the first power. So I'm erasing the x and the y, and I'm adding in numbers there, and I'm going to circle the rate law. This was worth 7 points. You got a point for comparing the concentration of chlorine dioxide. You got a point for comparing the rates of the same reactions. You got a point for determining that it was second order based on those two numbers. Same thing for 2 versus 3. You got a point for comparing the concentrations, a point for comparing the rates, a point for deducing that it is therefore first order, and then finally you get 1 point for your rate law expression. So that adds up to 7. And then part B, we're going to determine the rate constant. So we're going to take the rate law that we just determined, whatever rate law you determined, you just write it down. And then you're going to plug in numbers from one of the experiments. I plugged in numbers from experiment 1. I solved for K. And then these are the numbers from experiment 1. And you plug those numbers in. When you plug them in, I get 233.3, and that 3 goes on forever. The biggest mistake here is people didn't get the units right. Remember that this molar is squared, and then this molar cancels out with that molar. So you end up with seconds in the denominator and molar squared in the denominator. Significant figures here, it looks like the denominator numbers have 2 sig figs, and so I'm going to round this to 230, or 2.3 times 10 to the second. Molar minus 2, seconds minus 1. Oh, I forgot to do the points. This was worth 3 points. You got a point for rearranging for K here. Whatever rate law you used is fine, just as long as you plugged in your rate law from part A, or made up a rate law, whatever. As long as you put a rate law here and you rearranged for K successfully, that was worth 1 point. And then plugging in values from the same experiment was worth a point. You have to use all values from the same experiment. You can't mix up the experiments numbers, or else you're not going to get the right number here. and then 1 for the answer. So 1 for the answer means half for the units and half for the sig figs. Number 12, we have radioactive decay of plutonium-238. You start with 1 milligram. What mass will remain after 10 half-lives? And so you take your 1 milligram and you simply divide it by 2 10 times. Do that 10 times and you end up with 0.000976563 milligrams. Significant figures. The 1.00 that you start with has 3, except I accidentally wrote 2 and then I erased it and made it 3. So it rounds to 0.000976 or 0.000977 milligrams, depending on how you round 5. Either of those two answers are fine. Part B, if the rate constant is 0.0079 reciprocal years, what is the half-life? So you need to go back to page 1, and you're going to use this equation for half-life for a first-order reaction. T1 half equals 0.693 divided by K. You're just going to plug K in down here, and that's going to give you 87.7215. Significant figures. K only has 2 sig figs. This 0.693 has 3, which means we're going to need to round this to 2 sig figs, which is 88. And the units, that's the biggest mistake people made. The units are years. Units are time, because it's a time. T1 half, half-life is a time value. Or you can plug in, since this is reciprocal years on the bottom, it's in the denominator. So it's 1 over years, which is years. Okay. So 88 years is the answer. Points. Part A was worth 3 points and Part B was worth 3 points. So for the 3 points in Part A, you had to show that you understood half-life meant you divided by 2. You had to do that 10 times. That was worth a second point, and then your answer was worth a third point. For the half-life, you had to use this equation, which means that was worth a point to identify the equation you needed, to plug the values in correctly, and then, of course, to get the answer. That was the third point. Most people did pretty well on this. I was glad to see that because we didn't really do a whole lot of practice with it. Number 13, we have an integrated rate law question. Decomposition of dinitrogen pentoxide shown below is first order, and you're given the rate constant. So if you know it's first order, you need to go to the yellow sheet and get the integrated first order rate law, which is here. And we're going to plug in numbers. So K is given 5.1 times 10 to the minus 4. That's here, rate constant. 900 seconds is T. That's given here, 900 seconds. 0.950 is the initial concentration. That's here. That's usually the biggest mistake people make, is they plug that in accidentally in place of this one. So the sub-zero means the initial concentration. And then this is the concentration we're looking for. Is what is the concentration after this much time has passed? So you have to plug those numbers in. And you solve for that mathematically. You get that the natural log equals negative 0.51029. And then when you solve for the concentration of N2O5, that means you have to take e to the x. That's the inverse natural log function. So e to the negative 0.510293294. And if you plug that into your calculator, you should get that that value is about 0.600319. It says to round to 3 sig figs, so that's what I'm going to do. And the concentration is molarity, molar. So we circle that. Now this is worth 4 points. The whole question was worth 8, but part A was worth 4. So you get 1 point for just recognizing that you need this equation. So you have to write that down. You get 1 point for plugging things in appropriately. You get 1 point for mathematically solving whatever equation you used and plugged in numbers for. You get an answer for the mathematical solving of that because it's not easy since it's a natural log function. And then you get a point for the answer. So that should be 4. And then part B is how many minutes will it take to be reduced to 21.6%. There are actually a couple of ways you could have done this. You could have just used 21.6, multiply that by the initial concentration, which is 0.950, and you could have just plugged those two numbers in and solved for T. And that would have been, you would use the same equation used for part A. That wasn't the way we did this in class. The way we practiced it in class was we used the equation on the front page of your exam, which is shown here. Natural log of a at time t divided by a at time 0 equals negative kt. So that's on the front page of the exam. And then this ratio here is related to this 21.6. So this ratio is 0.216. because it's the ratio out of 1, not the percent out of 100. And you plug those numbers in, solve for t, and you get t is 3004.856615. Now, one little snag that I hadn't anticipated, I really honestly thought it said how many seconds. I didn't really pay attention. And the problem here is that your rate constant is in reciprocal seconds, which means your time at the end is actually in seconds, not minutes. I hadn't even planned on that being a little snag, and so it actually resulted in an extra point on the key because it's an extra step that I didn't really think we were doing. So you could have gotten 5 points on this part, on part B, instead of 4, 5 out of 4. So here you have to convert to minutes because the question asks for minutes, and had I noticed that before I printed the key, before I printed the exam and gave it out to you, I would have fixed it, but I didn't notice it. So we convert 3004.8 whatever 5661 seconds to minutes, and we get about 50.08. We round that to 3 sig figs, and we get 50.1 minutes. So as I mentioned a second ago, because I forgot that I hadn't anticipated needing this step here when I wrote the question, this part was actually worth 5 points. It was only worth 4, but you could have gotten 5. So you got a point for knowing this equation was important. You got a point for plugging things in correctly. Again, you got a point for the math because the math isn't necessarily very easy when you have natural logarithms. And you got a point for this conversion from seconds to minutes, and a point for the answer. Means you could have had 5 on this one. Okay, so let me know if you have any questions about that, and we can certainly go over it one-on-one if you need to.